The topic of today's lecture is velocity and acceleration analysis of planar mechanisms. Through velocity analysis, we obtain the velocity characteristics of all the links of a mechanism when the input velocity is specified. Similarly, through acceleration analysis, we obtain the acceleration characteristics of all the links of a mechanism when the input acceleration is specified. 2 points must be mentioned at this stage. One, that to carry out the acceleration analysis, velocity analysis must be completed first. And the second point is that both this velocity and acceleration analysis are carried out for a particular configuration of the mechanism. Just like displacement analysis, both graphical and analytical methods can be used to carry out the velocity and acceleration analysis. In today's lecture, we will present the graphical method. In this graphical method, we draw what is known as velocity and acceleration diagrams. Because it is a planar mechanism, the velocity vectors are two-dimensional. That means they can be represented by a two-dimensional vector. So the velocity of various points of the mechanism will be drawn as vectors after choosing a scale. That is, the length of the vector will be adjusted depending on the scale of the diagram. That means, suppose we choose 1 centimeter represents so many meter per second velocity. Similarly, for acceleration diagram, I will choose a scale such that 1 centimeter in the diagram will represent so many meter per second square acceleration. So we discuss velocity diagram and acceleration diagram. To bring out the salient features of drawing this velocity and acceleration diagram, let me start with a very simple example. For a slider crank mechanism at a given configuration, suppose the angular velocity and angular acceleration of the crank are prescribed. Our objective is to determine the velocity and acceleration of the slider at this particular instant, that is, at this particular configuration. So let us draw a slider crank mechanism, the kinematic diagram of a slider crank mechanism. Let us say O2A is the crank, AB is the connecting rod, and link number 2 is the crank, link number 3 is the connecting rod, and the slider is link number 4. The problem is that if we specify angular velocity of this input link, say the crank at this instant is omega 2, and I want to determine what is the velocity of the slider, that is V of the slider, which is body 4, which is same as the velocity of the point B. This is a particular configuration, and the answer, of course, will be valid only for this particular configuration. To carry out the velocity analysis, let me say, how do I draw the velocity diagram? We start from the input end, that is from link number 2. As we notice, the 2 points, namely A and O2, belong to the same rigid body that is linked to. We have already seen then, because A and O2 belong to the same rigid body, I can write velocity of A is velocity of O2 plus vector omega 2 cross the vector O2A. This is a vector equation. All these quantities are vectors, and because it is in 2 dimensions, each of these vectors has 2 unknowns, namely magnitude and acceleration. Such a vector equation is equivalent to 2 scalar equations, and we should be able to solve 2 scalar unknowns from this equation. So before we start drawing the diagram, I should ensure that this vector equation has only 2 unknowns. For example, here VO2, the velocity of this point O2 is 0, so both its magnitude and directions are known, because this is nothing but identically 0. Now here the input velocity omega 2 is specified, the vector O2A is completely known, so one can easily calculate this vector omega 2 cross O2A. So here also both the magnitude and the directions are known. I put a tick to indicate that it is known, and if it is unknown, then I will put a cross. For example, we do not know anything about the velocity of the point A, so neither the magnitude nor the directions are known. But from this vector equation, as we see, there are only 2 unknowns indicated by these 2 crosses, so I can use this equation to solve for both these unknowns. Once I confirm that I can use this vector equation, let me represent it by a vector diagram. We draw the velocity of the point A, which is 0 plus omega 2 cross O2A. This vector, I know the magnitude, that is O2 into O2A, because the vector O2 is perpendicular to the plane of motion and O2A lies in the plane of motion. So the angle between them is 90 degree. So the magnitude of the cross product is nothing but the magnitude of the product O2 and O2A. And the direction of this vector is perpendicular to O2A in the sense of omega 2. That is how we determine the direction of the cross product. So I can draw velocity of A, which is perpendicular to the line O2A. So that is, say, in this direction. So I draw velocity of the point A represented by this vector. While doing so, I have to choose a scale, because this velocity of A may turn out to be some meter per second square. So I choose a scale of the diagram, that 1 centimeter in the diagram represents so many meter per second velocity. So this is vector VA. Now I name the points in this vector diagram, which I call velocity diagram, as follows. This vector represents the velocity of the point A, so I write this point, indicate this point by small a. This is the capital point, capital A is the point A, and the velocity of that VA is represented by O2A. Both O2 and A I write in small letters. Now the velocity of A is completely known, so let us go up to the unknown destination, that is V4 or VB, through these motion transfer points. Now I consider 2 points, namely B and A, which belong to the same rigid body, namely 3. So I can write velocity of the point B is velocity of the point A, and both A and B belong to the same rigid body, namely 3, so I can write omega 3 cross AB. So this is again a vector equation where velocity of A we have completely determined, so I know its magnitude and direction. Velocity of B, I do not know the magnitude, but I know the direction, which must be horizontal. Because of this prismatic pair, the point B always moves in the horizontal direction, so I know the direction of the velocity B. Now omega 3 cross AB, I do not know as yet the magnitude of this omega 3, so the magnitude is unknown, but I know the direction of this vector omega 3 cross AB because I know the direction of both omega 3 and AB. So the direction is known. So again in this vector equation I have two unknowns, one here the magnitude of omega 3 cross AB and the magnitude of VB, and that can be determined from this vector equation. Now let me represent this vector equation graphically. I know that the velocity of the point B is horizontal, so it must be represented by a horizontal vector passing through O2. And omega 3 cross AB is perpendicular to the line AB, that is, it is in this direction which is perpendicular to the line AB. So through A, I draw a line which is perpendicular to the line capital AB. So this intersection of these two lines must determine the point small b such that O2B vector represents velocity of the point capital VB, which is, as we see, O2A vector plus vector AB, where O2A represents velocity of the point A and the line AB represents omega 3 cross AB. So I put a vector sign here and a vector sign there. So O2B represents velocity of B to the same scale which we have used earlier. So you see, we have determined the velocity of the point B, that is the velocity of the slider given the input velocity omega 2. Now before we go for the acceleration analysis, we must obtain all the information regarding the velocity characteristics. For example, now we determine omega 3 because I know this vector AB, small ab, this represent omega 3 cross AB, because this, so I can determine the magnitude of omega 3 because I know the magnitude of the vector AB, what velocity it is representing, and the magnitude of the vector AB. According to this diagram, the velocity of the point B, difference of the velocity of the point B and A is in this direction, in the upward direction, which means the angular velocity omega 3 must be counterclockwise. So we have determined both the direction and the magnitude of the angular velocity of link 3, that is the connecting rod. At this stage, we can start the acceleration analysis. For that, suppose we also give alpha 2. Let me draw the diagram again. O2, A, B. We have completed the velocity analysis for given omega 2. We have already determined omega 3. So omega 2, omega 3 are known at this stage, and we also specify alpha 2 let us say in the clockwise direction again. The question is, what will be the acceleration of this slider 4 or the acceleration of the point B? Given alpha 2, I have to find what is the acceleration of the point B. Now we draw what we call an acceleration diagram. To draw the acceleration diagram, again we choose a scale, that is, all the vectors will be represented to a scale that, say, some 1 centimeter in the acceleration diagram will represent some x meter per second square. This x is at our choice. We will choose a suitable value of x to draw a diagram. Again, we start from the input end and reach the output end, that is the point B, through the motion transfer points. So first we determine A and O2 are 2 points on the same rigid body 2. So I write A is A O2 plus omega 2 squared AO plus alpha 2 cross O2A. This relationship we have derived earlier, that the acceleration relation between 2 points on the same rigid body whose angular velocity is omega and angular acceleration is alpha. Now in this vector equation, AO2 is 0 because the point O2 is fixed, so it is completely known. This is 0. Omega 2 has been given, AO is known, so I know this vector completely, both its magnitude and direction. Alpha 2 is given, O2A is known, so this vector also I know both the magnitude and the direction. Whereas AA, I neither know the magnitude nor know the acceleration. So this vector equation again has 2 unknowns, and because it is only 2 unknowns, I can use this vector equation to draw the vector diagram. So first I draw acceleration of A has 2 components, omega 2 squared AO. So this is the direction of the vector AO. So I start from this point, acceleration diagram, and to the chosen scale I draw this vector to represent omega 2 squared AO. Then alpha 2 cross O2A, which is perpendicular to the line O2A, and this line is parallel to O2A. So I draw in the perpendicular direction this is omega 2 squared AO, and this vector is alpha 2 cross O2A. So these 2 vectors when added gives you the acceleration of the point A. So this point I start with O2 and this point I write A, because the vector O2A represents the complete acceleration, total acceleration of the point A. It has 2 components, O2 say A prime and A prime A. Once we have obtained the acceleration of the point A, I can determine that of the point B by writing AB as AA, because now we are considering 2 points A and B on the same rigid body 3. So I add omega 3 squared vector BA plus alpha 3 cross AB. I have already determined the acceleration of the point A completely. Omega 3 we have determined from the velocity analysis, both magnitude and direction. So I can determine this vector completely, both magnitude and directions are known. Alpha 3 is unknown, but I know the direction of alpha 3 cross AB, which is perpendicular to AB. So I know the direction, but not the magnitude. And acceleration of B again, because the point B is moving only along a horizontal path, the acceleration of B must be horizontal, so the direction is known, but the magnitude is unknown. So you see, again in this vector equation there are only two crosses, that is there are only two unknowns, so I should be able to use this vector equation to draw the vector diagram. So I draw omega 3 squared BA, that is a vector which is parallel to AB. So from A I go to a point, say I write it, I draw this vector. I do not know the magnitude because we are not using any particular numbers. So let this vector omega 3 square BA to the chosen scale become so much. I call this point B prime. This is the vector which is omega 3 squared BA. Now acceleration of the point B is horizontal, so I draw a line horizontal through the point O2. And alpha 3 cross AB is perpendicular to AB. That means the direction is known, it is perpendicular to AB. So at B prime, I draw a line which is perpendicular to AB, capital AB. So I draw this perpendicular line. So this perpendicular line drawn through B prime, perpendicular to the line capital AB, drawn through the point B prime is this line, and the horizontal line drawn through O2 is this line. So this equation suggests that the intersection of these two lines I can denote by small b, and O2b will represent the acceleration of the point B. Then only this equation will be satisfied. You see, A, which is O2A prime plus A prime A, then omega 3 squared BA, then alpha 3 cross AB will give you O2B, which is AB. So this vector represents alpha 3 cross AB. So we have completed the acceleration diagram, and using the scale of the diagram I can find O2B as acceleration of B. The magnitude of O2B is the magnitude of the acceleration of the B, point B, or that of the slider. If this diagram is correct, then acceleration of the slider at this particular configuration is towards left, because O2B is towards left. We can also determine the other unknown, say the angular acceleration of link 3 alpha 3, because using this vector B prime B, which is alpha 3 cross AB, and capital AB, the magnitude is known. So after finding what is B prime B, I can find the only unknown, that is alpha 3. If this diagram is correct, then what we find, that the tangential component of the difference of acceleration of B with respect to A is perpendicular to AB, represented by BB, and that is in the upward direction, which means alpha 3 is counterclockwise. Then only the tangential component of acceleration of B with respect to A will be in this upward direction. So alpha 3, we can find both the magnitude, which is magnitude of the vector B prime B divided by the magnitude of the vector AB, and in this particular diagram it is in the counterclockwise direction. So, we have carried out the complete velocity and acceleration analysis of this slider crank mechanism. I would like to point out certain special features. Going back to the velocity diagram, we start the diagram from the input end, which is the link 2. I start with the point O2. This point is called pole of the diagram. It is a velocity pole of the diagram, and we should also notice that we are using capital letters in this configuration diagram or kinematic diagram, whereas use small letters for the velocity diagram, and there is a correspondence: capital A, small a, capital B, small b, capital O2, small o2. And as we join all these points from up to the velocity pole, that is O2b represents the velocity of the point capital B, O2a represents the velocity of the point capital A. Similarly, in the acceleration diagram, this is O2 is the pole, capital A, capital B, small b. So, O2a, this vector represents the acceleration of the point capital A. And if I join small b with the pole of the diagram O2, that is O2b represents the acceleration of the point capital B. If we maintain this convention, then it will be very easy, particularly when the things get a little more complicated, there are too many vectors, to determine the velocity of a particular point of the mechanism. I just locate the corresponding small letter in the velocity or acceleration diagram and join that with the pole to determine the velocity or acceleration of that particular point. I hope this simple example makes the procedure clear, and for more complicated problems we need to develop a few more concepts. We have just now solved a simple example to show how do we carry out the velocity and acceleration analysis of planar mechanisms. At this stage, we will develop two more concepts which will be very useful, particularly when we have a little more complicated problem. We start with what is known as velocity image of a particular link. Similarly, we will develop what is known as acceleration image of a particular link. These image concepts will be very useful, particularly if there are higher order links present in a mechanism. We have seen in a mechanism all links need not be binary, there can be ternary, quaternary or other higher order links. When such higher order links are present, the concept of this velocity image and acceleration image will be very helpful. Another use of this image concept is if we consider an inverse problem. That means we have to locate a point on any link having prescribed velocity or acceleration at a particular configuration. What we have done earlier, given the input velocity, we have determined the velocity or acceleration of given points of the mechanism. But suppose for a given input velocity and acceleration, we want to determine which particular point of a link will have prescribed velocity or acceleration, then again this image concept will be very useful. Let me now develop this concept of velocity and acceleration image. Towards the development of this velocity image, let me consider a link or a rigid body, say, which is quaternary, and it is connected to 4 other links at point B, point C, point D and point E. The other 4 links which are connected here has not been shown. This is a quaternary link connected to 4 other links at points B, C, D and E. And say the angular velocity of this particular link is omega. If we draw the velocity diagram, we know there is something called velocity pole, and this O is the velocity pole. and B, C, D, E. These are the small letters representing these capital points, capital letters, capital B, capital C, capital D, capital E. So, if we join this point small b with the velocity pole, that is the vector OB represents velocity of the point B, the vector OB. Similarly, the vector OC represents velocity of the point capital C, and OD represents the velocity of the point capital D, and OE represents velocity of the point capital E. And this in the velocity diagram, this BCDE, this figure, small b, small c, small d, small e, this quadrilateral is called the velocity image of this quadrilateral consisting of capital B, C, D, E. Now, let me see what does this vector BC represent, the vector BC. OC is velocity of the point C, OB is the velocity of the point B. So, what does this vector BC represents? BC represents the difference of the velocity of the point capital C and the velocity of the point capital B. So, the vector BC is nothing but VC minus VB, because B and C belong to the same rigid body whose angular velocity is omega as assumed earlier, then this must be equal to omega cross BC. Similarly, CD, this vector CD will represent omega cross CD, which is nothing but OD minus OC, that is the difference of velocity of D and the velocity of C. Similarly, EB will represent omega cross EB, and DE will represent, this vector will be omega cross DE. In the configuration diagram, we had a quadrilateral BC, CD, DE, EB. We go back to the velocity diagram, we again have BC, DE, and let us see the ratio of these sides of these two quadrilaterals in the velocity diagram, in the acceleration diagram. Small bc is omega cross bc, small cd is omega cross capital CD, small de is omega cross capital D, and EB is omega cross capital EB. Thus, this quadrilateral BCDE is nothing but a scale drawing of the quadrilateral BCDE, and small BCDE is called the velocity image of capital BCDE, which is nothing but a scale drawing, and scale of the diagram is this factor omega, and small bc is perpendicular to capital BC because it is omega cross BC. So, this figure BCDE, each side is perpendicular to the corresponding capital sides, that is BC is perpendicular to capital BC, CD is perpendicular to capital CD, and so on, and this perpendicular is in the sense of omega. So, if we consider this quadrilateral BCDE and the corresponding quadrilateral in the velocity diagram BCDE, it is a scale drawing of the original capital BCDE, and it is rotated through an angle 90 degree in the sense of omega. If omega is counterclockwise, so this BCDE we can see to be rotated 90 degree in the counterclockwise sense because omega is counterclockwise. So the velocity image is a scale drawing of the original diagram capital BCDE drawn to a scale and rotated through 90 degree in the sense of omega, and the small BCDE is called the velocity image. This is called the velocity image of capital BCD. So if we know the points, 2 points of this quadrilateral, say BC, then I can easily determine the other 2 points DE by making a scale drawing. The same will be true even for the acceleration diagram. This is the acceleration diagram and this is the pole of the acceleration diagram O. So OB represents, this vector OB represents acceleration of B, and OC, this vector represents acceleration of C. So the vector BC, which is OC minus OB, is nothing but the vector BC is AC minus AB, where C and B are 2 points on the same rigid body whose angular velocity is omega and angular acceleration is alpha. So this we know omega square acceleration of C with respect to B, omega square in the CB direction. Plus alpha cross BC. So the vector BC is omega square CB plus alpha cross BC. As we see, BC prime is omega square CB, and C prime C, this vector is alpha cross BC. Summation of these two vectors give me the vector BC. So it is easy to see because this vector is parallel to BC and alpha cross BC is perpendicular to BC. These two vectors are at right angles to each other as seen here. So the magnitude of the vector BC is, because these two vectors at 90 degree, I can find by Pythagoras theorem that this is omega to the power 4 plus alpha squared into magnitude of BC. BC prime is omega square into BC, the magnitude. C prime C, the magnitude is alpha times BC. So using Pythagoras theorem, I get the magnitude of BC is square root of omega to the power 4 plus alpha squared into magnitude of BC. The same way we can prove exactly the similar way that magnitude of CD, this vector, will be omega 4 plus alpha squared into magnitude of the vector CD, capital CD. And this will be true for other two vectors, namely DE and EB. They are also multiplied by the same factor and the corresponding capital letters DE, EB. So what we see, the quadrilateral consisting of small letters B, C, D, E each side is proportional to the corresponding side of the quadrilateral consisting of capital BCDE. So, small BCDE is nothing but a scale drawing. The scale factor is given by square root of omega 4 plus alpha squared. This is the configuration diagram or space diagram BCDE. This is the velocity diagram BCDE. This is the acceleration diagram BCDE. And the small BCDE is always a scale drawing of capital BCDE, and the small BCDE here is called the acceleration image of capital BCDE. Like in the velocity diagram, this small BCDE is the velocity image of capital BCDE. This is the concept of velocity and acceleration image, and we shall see its utility in a later example. What we will find that if the velocity or acceleration of 2 points of a rigid body are known, then any third, fourth or fifth point I need not do an elaborate analysis. I can use this concept of image, which is nothing but a scale drawing of the original configuration or kinematic diagram. At this stage, let me now summarize what we have learned today. We have just started the process of velocity and acceleration analysis of planar mechanisms by drawing velocity and acceleration diagrams. We have seen that we have to start from the input end, where the input motion characteristics like velocity and acceleration given, and then go successively through all the motion transfer points to reach the output end, where velocity and acceleration have to be determined. We have shown it through an example of the slide air tank mechanism. Then we have also developed a very useful concept like velocity and acceleration image, which will be useful for mechanism having higher order links. What do you mean by image? That if we use the same convention of using small letters for the velocity and acceleration diagrams and capital letters for the configuration diagram, then for a particular rigid body, the velocity diagram and the acceleration diagram, we get a scale drawing of the original higher order links. The scale factor is omega for the velocity diagram and square root of omega 4 plus alpha square for the acceleration diagram, where omega and alpha are the angular velocity and angular acceleration of that particular higher order link. The velocity image is rotated at an angle 90 degree in the sense of omega, and acceleration image is also rotated from the corresponding space diagram, and that angle is not very important. You can easily find it out as an exercise.